Hello, SUSECon. I'm Richard, and I'm here to talk to you today about SLE Micro and openSUSE Micro OS and how it's a modern platform for all computing in this day and age. A little bit about myself. I've been a contributor to the openSUSE project since before it began. I've been at SUSE now since 2013. Before that, in my past life, I was a systems administrator working in academia in the UK. Inside SUSE, I've been a QA engineer. I've been part of the openSUSE board. These days, I'm a Linux distribution engineer, mostly working on rolling releases such as openSUSE Tumbleweed and openSUSE Micro OS. But in addition to that, I do some consulting directly with some SUSE customers who are now implementing SUSE Linux Enterprise Micro in their environments in the real world. And in my spare time, I dabble in a bit of photography. So I'm here to talk about what is MicroOS, but I think before we get sort of into the technical details, it's better to kind of explain why is MicroOS and SLE Micro? Like, why do we need a different type of operating system in this modern day and age? And really, at its heart, it's accepting the fact that computers in 2022 are not the same as they were back in 2000 or 1990s. We're not just talking about laptops, desktops, and servers these days. And even when it comes to laptops, desktops, and servers, the way people and the way enterprises use these devices, want to manage these devices, need to handle entire fleets of servers or server instances or VMs. It's a very different way of working than it used to be 10, 20 years ago. And MicroOS is really aiming to sort of address a lot of the issues that come out of that. Perfect example would be, IoT, small devices like these IP webcams or other similar IoT devices. I'm recording this at home. I'm surrounded by them here, and anybody who's ever updated it knows, these updates are fraught with issues. And in many cases, they don't get any updates at all. Lots of these devices don't have any updates. They're prone to getting malware infections. They're prone to being parts of large botnets. But at the same time, it's kind of some way understandable why companies don't update these devices, because if something goes wrong, there's millions of their customers potentially that they're going to break. The risk of what if something goes wrong with these updates is really quite large. Perfect example of sort of this gone wrong on a humongous scale, not just in IoT, but sort of embedded computing, was in 2019, the O2 UK network update. Basically across the UK, the O2 telecom company have their cell towers, giving you your 3G, 4G, and 5G networks. Although this wasn't 5G then, of course. And, they wanted to update the cell towers, update the embedded devices in there, and that was just done as a over-the-air firmware update. And the over-the-air firmware update was rolled across to their entire fleet of cell towers, and then one by one, every single one of their cell towers stopped working. And not only stopped working, but also stopped working on the management interfaces, and also had no way of them rolling back the firmware update they had just done. So they pushed out this update to their entire network and lost their entire network. Every single person in the UK suddenly didn't have any O2 network coverage. And because there was no way of recovering automatically, the firmware was there, it was done, it was booted, and nothing was talking to it anymore. Their only solution was to literally send all of their engineers manually, physically out to all of their cell towers, and hence the picture of a person climbing the tower here, and having to manually connect a laptop and manually reflash the tower and manually get the tower back into the network and everything working again. At SUSE, we were looking at this and thinking about what we already were doing with SUSE Linux Enterprise and the like, and realizing traditional Linux operating systems are potentially part of the problem with stuff like this. You need to have a really reliable update stack. A mechanism of updating the system where everything is changing from a perfect, from a known state to another known state, there needs to be some way of validating, does this state actually work? If it doesn't work, then it needs to be able to automatically recover, because you don't want to be sending an engineer out to the field to fix it when it goes wrong. And all of this needs to happen as quickly and as smoothly as possible, because outages can be very, very expensive, and any repair can be incredibly time consuming. When we're also thinking about this, looking at edge devices as well, the end, in this case, we kind of describe, using edge as an example with trains in Germany. One of these trains is basically a data center on wheels these days. We're talking about the requirement to be running 99% of the time. A lot of these trains are leased, and the leasing company needs to have a good awareness of how is the train doing, where is it, what's it doing, how are the devices inside there working. So you're talking about 300 odd sensors producing a huge amount of data across hundreds of trains, billions of data points, terabytes of data a year, most of that needing to be analyzed in the train itself, because you're talking about trains that are moving across the country. There's uplinks. They can use things like cell phones, cell networks to provide some data back, but you're not going to be transferring terabytes across that while the train is moving. So lots of local analysis required, but so the train can be aware of its own health. What are the status of the components? How is everything working? How is it interfacing with the rest of the train network, the signals and the barrier detection and the like? And then also even have some way of smoothly uploading all of that, and analyzing it to some cloud elsewhere. And of course, if you look at the requirements from the OS side, it's a very similar story to the embedded or IoT environment. You need an operating system that can take care of itself. You need an operating system that can patch itself, repair itself if something goes wrong. Even harder to send an engineer out to a train, because the train's probably moving around and you might not necessarily know where it is if the uplink has suddenly gone wrong, which is a terrifying thought, really. But also, there is a case to be made that this kind of way of looking at operating systems makes sense also for the traditional data center. We've been doing data centers for decades, but our data centers have been getting more and more dense with more and more instances. Either more and more servers or more VMs running on existing servers. You're talking about a big management issue, and there's some really cool tools to manage large networks of large clusters of large amounts of instances. But wouldn't it be good to have an operating system where, in many cases, you don't need any of that management? If you're going to have an entire farm all running the same OS, why can't that OS also be responsible for patching itself, be responsible for rolling back? And if you think about workloads being containerized, either in OCI containers running on the hosts or running in Kubernetes clusters, you can really see there's a need there for automatic updating, automatic rollback, and basically being sort of the perfect kind of cattle operating system. We've been treating our systems like pets for decades, carefully maintaining them and managing them and grooming them, but that doesn't necessarily scale out to the numbers we're dealing with these days. So having an operating system which takes care of itself as much as possible, and then if something goes more complicatedly wrong where it can't deal with it itself, it should be easy to just rip and replace and put a new one in there, rather than having to manually get the machine back up and running. And so that's really what we sort of were looking at with SLE Micro and MicroOS. The cloud is a reality these days. More hardware is normally just a credit card transaction away when you need it to make to start scaling out your data center. At the same time, on the IoT side of things, we're seeing more and more single-purpose devices out there. Containers really open the door to limiting the incompatibilities between services, or being able to maybe offer more than one version of a service on top of a host at the same time, because those services are isolated from each other. So also when a problem goes wrong, you're only talking about impacting the container and the other services talking to that container, not necessarily the entire operating system. And also with virtualization, of course, we see more services, more VMs, even when you're talking about more physical hardware. So When we were looking at this, we realized, if we're talking about large scale, really, you need to start by having the operating system as trim as possible, as small as possible, minimize the need for update, minimize the changes, minimize the need for configuration, and make it as small and easy to roll out and roll it out repeatedly and at scale, potentially over smaller links. Also, you need an operating system that is far more predictable than your traditional Linux. You know, changing a potential opportunities for variation or unexpected modification. So it should run the same way on every single boot while it's operating. It shouldn't be alterable. Hence using things like read-only root file systems, and the system should be customizable by the user on deployment. This sort of assumption being, we might be providing sort of pristine images, but then the customer can deploy their variations on top as part of the deployment, rather than necessarily having to make custom images themselves, for example. And all of this should be as reliable as heck, especially when we're talking about the kind of environments we've been talking about so far. So automatic updates, automatic rollback if something goes wrong, and leveraging things like containers. So the base operating system and the workload are two discrete, separate things. And like I've already mentioned, regular Linux just isn't good enough for this. Nothing's it's kind of sad to say something like that when I've been working in traditional Linux for so long. But Linux, as we typically think of it, was built as a Swiss Army knife. A single operating system that can do a little bit of everything, and you can customize it and tweak it and tune it. But a Swiss Army knife isn't necessarily the best tool for every job. It's a tool that can do every job. With MicroOS, we're looking much more of being able to provide much more refined tools, scalpels rather than Swiss Army knives. And that complexity of traditional Linux brings a lot of baggage and potential issues with it. The more services are on a machine, the more chance there's going to be incompatibilities between those services. The more different versions of libraries on the machine, the harder it is for that system to be maintained. The harder it is for that system to be updated. How harder potentially to put the service on top that you want to put on top of it. And then when something does go wrong, the troubleshooting and complexity of trying to figure out why it's gone wrong, where's it gone wrong, is far more with a system built like that, because there's a lot of moving parts, there's a lot of components that could go wrong. It's a complex mess. That's part of the reason why you buy SUSE Enterprise, to make that a little bit simpler. But the next step looking at this really is, why not make the operating system simpler, just fundamentally? In many cases, customers, users already know this. They take regular Linux, they take SUSE Enterprise, they take openSUSE, and then try and make it a little bit simpler for them in their environment. Like making their own custom images, deploying it often in very single-purpose VMs, rather than sort of the old clunky idea of a server that could do 4 or 5 things at once. Minimizing the amount of services that are installed. Quite often, a lot of customers ignore patching of their host and instead just rip and replace, and then redeploy, which is sometimes seen as a good thing, sometimes seen as a bad thing. You want your system to be patched, surely. But then if you're going to be replacing everything every couple of weeks anyway, what's the risk? Potentially. And quite often, rather than micromanaging an entire fleet of systems as we start scaling out to the scenarios we're talking about, you see people quite often, just adding more instances rather than necessarily going back and fixing previous instances or patching previous instances, which can be a management issue over time. But it does just really show how users are thinking about this, of wanting to try and simplify the problem for themselves. But handcrafting, as we see out in the field, isn't good enough. It is an incredibly hard challenge to build a single purpose system by hand and do it right. We've spent an awful lot of time working on MicroOS and SLE Micro. It's not been easy, and doing that on top of a traditional Linux where it's been built very, very differently without these things in mind, it's even harder. Even when you do it well, there's still issues with configuration management. How do you manage the all of the varying configurations on top. How do you keep them in sync with the base OS and the like? There's still an awful lot of effort to keep the whole thing patched, and maintaining it, optimizing it for CPU, disk, and RAM is an incredibly hard task, especially as things move on and new types of CPU come out and disks get more complicated with NVMe's and the like. It's hard work. It's really hard to do it if you're on your own. It's even harder when everything is moving around you at the same time. And even when you do it perfectly, no system is ever perfect. No operating system is ever perfect. There is always going to be flaws. There's always going to be the need for patching. And sometimes those patches are going to go wrong. Nothing is perfect. We try our best to be, but nothing is absolutely perfect. But therefore, if you have an operating system that accepts that fact, that accepts that, okay, even though we've minimized the risk, even though we are doing things incredibly carefully, even though we have great testing, great quality control, and we're testing everything 6 ways backwards whenever we can, something can still go wrong. Then have the operating system be able to detect that itself, repair it itself, and undo it itself. Basically, following this idea of if it was worth doing in the first place, make sure there's a way of undoing it, so the system can go back to when it last worked. And this is really sort of the philosophy behind what we've built first as openSUSE Micro OS, which is a predictable, immutable operating system. Once it's booted, the running system doesn't get altered. It's reliable. It has automatic updates. It has automatic rollback when something goes wrong. And the installations are kept as small as they need to be, just to do one job. Quite often that can be containerized or sandbox applications. More about that in a bit. And of course, we've been doing this in openSUSE for a while now. And alongside that, there is SUSE Linux Enterprise Micro, which is basically the SUSE commercial companion to openSUSE Micro OS. Just as predictable, built on a SUSE Linux Enterprise codebase. It's the same thing, just better and more stable in some respects. The MicroOS architecture, I keep on referring to MicroOS because it was the originator of all of this, but the terms really are interchangeable just depending on the code base. MicroOS is a rolling release built on top of the openSUSE Tumbleweed rolling release. The entire thing is built, developed, and tested as part of the Tumbleweed release process. So if Tumbleweed has a bad day, MicroOS isn't getting released. If MicroOS has a bad day, Tumbleweed isn't getting released, which is an incredibly nice way of keeping sort of both the traditional and the modern way of doing things sort of honest and also in sync with each other. So we get the benefits of both in many respects. And with SLE Micro, it's a regular release, with a different cadence from standard SUSE Enterprise, but definitely a slower cadence than openSUSE Tumbleweed, based on the SUSE Enterprise codebase, inheriting its packages from SUSE Enterprise, inheriting its updates from SUSE Enterprise. Our MicroOS images are pretty small and constantly shrinking. I'm pretty sure since I did this slide, they shrunk a little bit more, which is quite nice. But basically for a bare metal install, so an installation on regular hardware out in the real world, we're talking about just over 600 megabytes. And a huge amount of that is the hardware enablement that you need in the kernel that we really can't do anything about because we don't necessarily know what hardware this is going to be installed on. So, almost 200 meg just for the kernel, another 150 meg for the firmware. We can't do anything about the bootloader. We need to have a bootloader that can handle all your hardware. So again, that kind of takes up a huge chunk, and then our contribution for the rest of MicroOS and user space is pretty small in comparison. On a VM image where we do have a much better idea of what hardware is there, we don't need a very large kernel. We can use our base kernel. Things are much, much smaller. It's under 400 megabytes now. Altogether, we're talking about really just 210 source packages, so an awful lot less than your typical installation of any SUSE Enterprise, SLED, anything like that. Wanted to just take a quick step away from the technical for a bit to kind of share the mindset I think that is best to think about when deploying MicroOS and SLE Micro. Where it's a different operating system. You've got the idea of where we're coming from when we're building it, and now when you're deploying it, I think it's better to realize, you're not installing a traditional Linux, and you don't necessarily need to think about it in the same way. This was designed to be a single purpose operating system. So, we're expecting each microOS instance to be installed just to do that one job. That one job might be running containers, and those containers could be doing multiple jobs, but the OS itself, it's there to do a single task. This is how we scale it for doing things like IoT, and then for Kubernetes or regular containers. Generally speaking, we're assuming that whatever workload that is going to be, we're expecting it to be containerized. There's exceptions potentially for an IoT device. It could just be a traditional application on top. But generally speaking, it's better with microOS to be thinking in terms of containers or Flatpaks or something like that, some abstraction layers. So the container, your workload, can be managed, updated separately from the operating system, which means, again, you can forget about the operating system, which is kind of the point. microOS is meant to be just set it and forget it. You shouldn't need to go diving into a microOS instance once it's deployed and going in modifying configuration heavily once you've deployed it. You should just be able to deploy it, forget about it. It should be able to update itself, and everything should be fine. If something doesn't go fine, it should be able to self-heal itself. And if it can't, it should be easier for you to just redeploy everything to get exactly back to your working state rather than digging around manually repairing it. Like you could, with SSH is still there, you can still connect to these machines. But in terms of sort of the mindset, we're building this with the idea of you shouldn't need to be doing that. We have the tools, the technology to just be deploying all of this stuff automatically, not needing any management, not needing necessarily any even remote management, because these machines could be out in a field where they haven't got any way of calling back home. They should just work, take care of themselves, and then, should be relatively easy to fix it if it all goes wrong. Part of that is also, this concept of, you never want to touch a running system, which I think, as a former sysadmin myself, I definitely felt that way, especially on a Friday afternoon. And we've really embraced that when it comes to how package management works on SLE Micro and microOS. With transactional updates, our update stack, we are ensuring every single update is atomic, as in, the entire update applies, the package and all of the other packages and every dependency and everything all happens at once, or nothing happens at all. It doesn't, it's all or nothing. No partial installations, no scripts maybe doing a little bit of something. But all of this happens in a way where the running system never gets impacted at all. Once it's running, you're running on that known state, and you're staying on that known state for the entire lifespan of the boot of that system. From a user's point of view, if you're familiar with regular SLE and snapshots, you might have seen slides like this already, but we basically use very similar technologies, but approach it in a very different way. Rather than having the existing system, patching that system while it's running and creating snapshots so you have some kind of checkpoint to go back to, with transactional updates, we only move from these known states. So there is a read-only snapshot that shows the last boot. Before that, there's another one that shows the boot before, etc. And then, you're running from some current boot that you're in right now. When an update happens, normally automatically triggered by a systemd service, which we install by default. So normally you're not doing this interactively, because that wouldn't make sense with the mindset. It creates a new snapshot, which is a standard read-only clone of the running system. It will make that snapshot read-write. The updates will be done using the regular zipper command and regular zipper package management, but instead of happening on the running system, it happens in that new snapshot it just made. The snapshot then gets marked as read-only again. And then, in essence, we are kind of misusing the rollback functionality of Snapper to roll forward to mark that new snapshot we just made to be the next boot target. So when the system reboots, you're atomically moving, no matter what the package manager did, no matter what the RPM scripts had to do, no matter what weird modification might have been needed to be done, you're effectively moving from a known system image that you booted to a new system image, which, okay, was created by package manager, but it's in essence a new system image, which you're rolling forward to on the next boot cleanly. So after the next boot, you're running on your new system image, and you have now an extra version of the previous images to roll back to if something goes wrong. Without rebooting, you potentially can have a situation where you've got 2 or 3 different system images, where potentially you could have a bunch of updates in one, a bunch of different updates in another one, and in one in third. That only happens really in this day and age if you're going involved and doing what you shouldn't be and interacting with it manually, because automatically we can actually have transactional update now update the unfinished snapshot that it was working on. But I just wanted to mention if you are doing manual transactional updates and not using the continue flag in transactional update, you potentially can be created a situation where your first set of updates never really get applied because you applied a second pair of updates and you booted into that second pair, and the first pair never got written to the system in a way that it's going to be used. That snapshot just never gets used. So use the continue flag when you want to avoid that, if you are managing all of this manually. As I mentioned, all of this is powered by BTRFS. Some of the reasons for that, compared to, let's say, doing A/B disk partitions with big clunky disk images, is this is incredibly space efficient. You're not using half of the disk to carry one copy of a previous state. We're able to carry many copies of many previous states because each snapshot is only containing the diffs of each various snapshot. All of the configuration files are also be able to be captured as part of that. So, you're not just rolling back the system image to the previous state, you're able to also roll back the entire configuration to the previous state, which is very useful if your new system update required you to modify some configuration and then, something went wrong. If you do roll back just the binaries and the libraries, your configuration could now be wrong and you've just created a situation that's worse for yourself. So you get a lot of the benefits of an image-based update of moving from known states to known states, but without the limitations. Also, sort of avoiding limitations or complications, you're able to do this with traditional RPMs. So third parties wanting to build stuff for SLE Micro or MicroOS, you can build them the same way that you currently do with SLE. I mean, it's the same RPMs, the same repository management behind the scenes. Nothing new there. No need to learn something like RPM OS tree. No need to really handle anything differently. Just following the standard basic rules, which really you should have been following if you were doing it on SLE anyway, like writing to the correct parts of the file system. But yeah, nothing new or special there for us or for third parties building for the platform. There's no size limitations because compared to A/B partitions or image-based updates, you quite often have a very strict limitation on how big these partitions must be and or how big they could be. None of that. BTFS, we can scale it up, we can scale it down for tiny machines. With tiny instances, of course, you need to make sure the MicroOS images is nice and small, but you've heard how small they are, so you can quite easily keep a trim couple of snapshots on a very, very small machine and things will still work fine. And all of this is sort of very easy to enhance because we're basically basing this all on known, safe, long-use technologies in the SUSE space. Also, very easy to roll back. If you do need to manually go back into a system and the automatic recovery did not work, it's simple as going into the boot menu and picking a previous snapshot. And that also means there's no fancy user space tooling, which also means sort of the threat surface for a boot blocking issue is very, very small. We're not having to worry about, for example, did we accidentally break our B partition's kernel and or something like that. We just have to make sure we keep the bootloader working. Lowers the risk, keeps us all running far more stably, far more smoothly. If there isn't a reason for something to go horribly wrong, then rolling back is just a case of picking that previous snapshot. So it's immutable. Nothing's changed. It's been read-only the entire time. Everything's back to exactly how it was. This can be done as often as you want. So you can always go back to a known working good state, or even a previous one, or even a known yield. This can be done automatically. We have a tool called Health Checker, which by default just checks the basics of has the service booted, but you can very easily extend it yourself with your own plugins to look very, very detailed into is your very specific workload working exactly as it should be. If it isn't, then Health Checker can immediately flag its freshly booted snapshot as a bad snapshot and also automatically roll back. Even if it did work the first time, but didn't necessarily work the second time, Health Check is smart enough to go, okay, this is weird. I'm on a snapshot that isn't new, but I'm suddenly having boot issues. Then it acts a little bit like a sysadmin would. By default, it will just reboot. It won't actually roll back the first time. The first time it's had an issue on a known good snapshot. But then, if it is failing again and again and again, then it'll shut down and inform an admin because you've got a situation that's sporadic and weird and unreliable, and that's totally against what we're trying to do here with SLE Micro. We want it to be always staying in known good states the entire time. There is a slight limitation, of course. It needs access to the hard disk, so if the disk isn't there, then things aren't going to be working. But then if the disk isn't there, you're probably not booting in the first place. So you've got a bigger issue to be dealing with. You can't. How can software really fix that if sort of the fundamentals of which parts of the machine are available suddenly aren't there? All of these is done in the traditional SUSE, openSUSE way of making sure the entire supply chain and update stack is nice and secure. All of the updates are delivered via HTTPS. All of the packages are signed. All of the repositories are signed. So you can't have a situation where some of the packages are being swapped around by an intruder with old insecure ones. All of this is verified automatically by transactional update as part of the update process. And if none of these verifications fit, or any of them go wrong in any way at all, then the entire snapshot just gets thrown away. It never gets booted to. Nothing happens on the system at all. In terms of hardware requirements, SLE Micro and MicroOS share them the same. It works on ARM and x86-64. And I believe also actually AS390. I should have updated this slide, sorry. On ARM, we support both EFI, either firmware or U-boot. And on x86-64, we have images for both UEFI and for legacy BIOS. In terms of memory, we're perfectly fine with as little as 512 megabytes. And in terms of storage, we can go lower than 5 gigabytes for the root file system, and we can go lower than 5 gigabytes for the var file system. But we say that is kind of our recommended starting point, where we don't really have to worry about asking awkward questions like, okay, how many snapshots do you want to keep? How big are your workloads? If that's a good starting point if you don't know where you want to start with SLE Micro or MicroOS. In terms of how you can deploy MicroOS and SLE Micro, we have DVD installations with YAST. We have Yomi, a tool using SaltStack, where you basically your SUSE manager instance or your Saltmaster can have the configuration in there of how you want your SLE Micro image to look. You boot into a pre-boot Pixie environment. It connects to the Suma server, and your instance gets created out of thin air using Salt, which is quite fun and impressive. And we have, of course, images pre-made for VMs, Vagrant, Cloud, Raspberry Pis, etc. And then those pre-made images are expected to be updated and configured on their first boot using tools called Combustion and Ignition. Ignition comes originally from the CoreOS space. and was intended as a sort of partial replacement for Cloud Init. By the way, we do actually also support Cloud Init, but we typically only use that in sort of public cloud environments where you have to use it. Ignition is typically better for most of the use cases you're thinking about with SLE Micro and MicroOS. It has sort of all the basic features you'd expect of a sort of first boot configuration tool. It can partition the disks, it can format those partitions, writing basic configuration files, enabling systemd services, configuring the users, SSH keys, that kind of thing. All of this runs out of the init-ramfs on first boot. And unlike Cloud Init, which used to drive me crazy, it doesn't touch subsystems that you don't explicitly mention the configuration file. So there's no like random defaults that it might suddenly get. You're going to be getting just what you put in that configuration file. So if you want to configure SLE Micro with a sort of a nice, clean, structured configuration file, Ignition is the way to go. But there are some limitations with having a nice, clean, structured configuration file. Basically we realized, there's times where you need to do a little bit more sort of free-form configuration of the machine on first boot. Things like creating completely additional files anywhere in the file system, installing packages, setting up hardware devices, repartitioning the existing disks, that are already there, because Ignition won't touch anything that's already got data on it. And so we created this tool called Combustion, which basically also runs on the init system this time out of Dracut, and can basically just runs as a bunch of bash scripts on that first boot. So anything you can model into a shell script, you can do with Combustion. This actually ends up being sort of incredibly powerful and incredibly useful. I think every customer that I've worked with always ends up using Combustion because you quite easy to just have a small sort of library of your Combustion scripts for how you want your images to look, and then your SLE Micro instance is going to boot up, get the Combustion script, run, and your system straight out of the box works perfectly fine, exactly as you want. On a SLE Micro MicroOS instance, you're going to have a situation, of course, where you need to debug issues on the system potentially. If you are dealing with the machine interactively, then there's going to be times where you need to get a little bit down and dirty with the system. But of course, that system is a read-only root file system, so you can't just install some debug tools to figure out what's going on the same way you could on a traditional Linux machine. And you don't necessarily want to be doing a transactional update, putting the debug tools in a transactional update, rebooting, and then, well, the problem you just were looking for is gone because you rebooted, right? So we have a tool called Toolbox, which allows you to basically have a nice, persistent, privileged, or if you want, unprivileged, but in terms for debugging, that doesn't necessarily make too much sense, privileged runtime environment running in a container, which is a read-write standard, in essence, almost a virtual environment, able for you to poke around the running system, install what packages you need interactively on that system, just using zipper like usual. You can browse the entire file system, you can see the device tree, you can do everything you need to do to figure out what's going on wrong with the system. And then if you want to keep the toolbox on that system, it's persistent, the container's still there. Alternatively, you can delete the container when you're finished with it. And if you haven't modified anything on the running system, so it's all nice, clean, and back to where it was. So in my case, I've really caught the MicroOS and SLE Micro bug. I no longer use any traditional Linux at all. This entire presentation. That's skipping ahead. But all of my servers, which previously were using things like Tumbleweed, Leap, or SLE, are now just MicroOS. All rolling, all using the Tumbleweed code base. My personal blog is running Jekyll. That's running in a container from the upstream Docker Hub container. It updates itself, it patches itself. I honestly cannot think of the last time I actually looked at that machine. My website's still up, so that's all good. My Nextcloud, all of my file storage at home, same thing. It's a little MicroOS box just sitting in the corner here. Again, I can't think of the last time I ever did anything with it. I know it's still updating. I do occasionally pop in just to make sure that it is updating, but there's never done anything wrong with it. It's just there, it works. The Nextcloud containers are running on there perfectly fine. My TV has a retro gaming emulation station running in the back of it. There's a Minecraft server, which actually is, I think, now the sort of SUSE official Minecraft server for developers at SUSE. Again, microOS instance running on the public cloud. It just sits there. It just works. It's running everything in a container. I don't have to worry about it anymore. I do have a Raspberry Pi sitting next to me too, which I've set up as a network monitor, which is kind of fun and pointless because, well, none of this ever breaks. So the network monitor never actually tells me that something's broken. But that itself is also running microOS. There's a post on my blog about how I built that, how I did combustion. It's kind of a good introduction to anybody wanting to sort of see what you can do with combustion, because this is just, straight out of the box, microOS image, everything done there. I've redeployed this a few times just to kind of prove that you do. It's a really nice way of working. And like I mentioned, or almost gave away, even this entire presentation has been done on microOS because there is now a microOS desktop also. This is now my desktop operating system of choice. That's the one job in the case here. Because desktops are a little bit different, that does mean that the base OS is a little bit different than regular microOS, because we're not dealing with a server workload there, we're dealing with a desktop. So the base system has to be a little bit bigger, because it now includes a desktop environment and all of the basic configuration tools. So if we're talking about, in my case, where I'm running GNOME, that's Wayland, GNOME, everything there, that's provided by regular operating, as part of the regular operating system. But then everything else, all of the applications, the LibreOffice that is being used to do this presentation, the browser that I use every day, all being provided as Flatpaks from FlatUp. Just, they work, integrated into the software store, built into GNOME software. I can just add new software just like that. It downloads it from Flatpak. It installs it into my home directory. It just works. But it was designed kind of sort of very particular, for a very particular view. All of the stuff I've been talking about with the microOS mindset and why we're doing this. I know it doesn't appeal to everybody. So the microOS desktop isn't for everybody. It's, people like me, lazy developers who just want a desktop that works and always works and doesn't, get in the way of what I'm doing. It's especially useful if you're developing around containers, because you end up using containers for everything every day. I no longer use the shell baked into the operating system as my sort of daily shell for interacting with stuff on my system. I have a toolbox, and that toolbox is where I have my VI and OSC for interacting with the build service and all that stuff. Potentially, though, there is a kind of a weird crossover between lazy developers and kind of the grandma of lazy developers. If you think about what companies like Apple do and Google do with like Chromebooks and iOS, they have a very similar philosophy behind, having a very cut down system with a very particular base OS moving in a very particular way. In this case, they're doing firmware updates, but why couldn't that be transactional updates on a microOS desktop and have a very sort of curated, locked down, automated and reliable base OS than the applications coming from something like FlatHub, which is a much more kind of user-friendly way, or at least how users are now used to dealing with desktop applications, because, well, that's how they get it on their phones, that's how they get it on their tablets. Why can't they get it on their Linux desktop that way? Why do they have to learn how package managers work and all of that funky stuff? So the goals of the microOS desktop project is basically, do microOS, reliable, predictable, immutable OS, but for a desktop. It's going to be less customizable. It is less customizable than regular Tumbleweed or Leap. It is small, but not so small as the couple of 100 MB we were talking about earlier, you need to have a fully fledged desktop. So you need to have all of the hardware support for printing and all of the hardware support for gaming and all the stuff you need for media production, like this presentation. All of that should work, and all of that should work out of the box. You don't want to be messing around, spending days getting your MicroOS desktop up and running. Admittedly, I haven't needed to redeploy this thing since I deployed it, but if something did ever go wrong with this, I like the idea of being able to just put the image back in and get back to where I am, way easier than you would on any other desktop operating system. In terms of the status, the project is, well, in the case of the GNOME MicroOS desktop, is in beta. It's not quite perfectly there yet, but we do have images that are reliable, predictable, immutable. They are less customizable than your traditional Tumbleweed or Leap. It is small, but fully featured. Does have complete support for printing, gaming, multimedia, as you can see me here. The main problem at the moment is we don't quite have it working out of the box as cleanly as I would like it to be. Things like the transactional updates happen invisibly in the background, and I don't really want them happening invisibly in the background. This is a desktop operating system, so we're working on things like having a notification for the user that your system's updated, please reboot. Otherwise, if you left your MicroOS desktop running for days, you're never going to be getting updates, which it'll be nice and reliable, but it won't necessarily be secure. So when I talk about MicroOS, there's always one myth that pops up every time, because I've mentioned containers, and it's like, well, and I've mentioned it being small. So it's like, okay, you've got a small operating system that does containers, so you have MicroOS containers, right? And no, because MicroOS isn't an operating system to be inside your container. It's meant to be your operating system on your host in your instance, which may be running containers. You just don't need MicroOS to be inside a container. We already have that perfectly covered in the SUSE ecosystem, with the Tumbleweed containers or with the SLE BCI containers. The Tumbleweed containers are less than 100 meg for kind of your big, chunky, fully featured, heavyweight container that can do everything. And when you're talking about tiny stuff, it's less than 10 megabytes. The SLE BCI containers are also less than 10 megabytes, and even their base container is smaller than the chunky Tumbleweed one. So, those are the right operating systems. They're the right toolkits for being your container operating system. But while I'm talking about containers, it always comes up that, what about Kubernetes? In the past, we did have a project in the openSUSE project called Kubic, which was MicroOS with community Kubernetes atop it. The project still currently exists, but I'm actually in the process of winding it down. And the main reason why I'm winding it down is K3S exists. And K3S is the perfect Kubernetes for running on top of SLE Micro and MicroOS. And it exists, and it takes 30 seconds to install it using the documented steps from Rancher. You get it straight from them. It downloads, it installs perfectly fine. There's no additional customization or complication required. It understands transactional updates, and it still supports the SE Linux that we're using in both systems straight out of the box. So it just works, which kind of fits in with everything else we're trying to do here. So if you're interested in sort of joining, especially the openSUSE MicroOS side of things, we're available on the internet. That is the current mailing list, formerly for the Kubic project. There will be a new mailing list soon, but if you join there now, when everything renames or whatever, that's where we will send where things are going to be. And please feel free to keep in touch, give your feedback, get involved, and have a lot of fun. Thank you very much.